So it's an honor to be here, and thank you for the invitation. I'm really looking forward to spending the next half hour talking to you about how data and computation on that data is really changing not even just the auto industry, but virtually every single industry. And what we've seen now really is a whole shift in how computation is being performed. And moving from serial to parallel processing has been fundamental to this. This has implications everywhere, and what I want to do is talk a little bit about how data is at the foundation of everything that we do and coming up with new computing models on that data. Part of what we do as a visual computing company is talk about how do we simulate reality? How do we take data? How do we learn from that? How do we augment real data with simulated data and learn from that? And now, most recently, of course, the whole shift is on how do we understand what's going on around us? How do we take data and make sense of it? And so that's really what I want to focus on. Many of you probably know NVIDIA started a long, long time ago as a graphics company, and specifically video games, right? And this was state of the art when we started our company over 20 years ago. It was all about driving, and this was our automotive business, right? It was all about driving. Fast forward now, what we're at is a area where this is what a driving game looks like, right? This is using real data. This is using physics computation. This is rendering real materials, right? Trying to simulate reality. How do we manage the physics? How does light behave? All of this, kind of has been pioneered in gaming and now moves to other industries. So again, in the automotive space now, what we see is a lot of this technology being used in the design of vehicles. This is Mercedes-Benz using physics simulation, being able to do virtual wind tunnels to figure out how to make a more fuel-efficient vehicle. In this case, this was a concept car from the Frankfurt Auto Show recently, and this was actually a transformer vehicle. So the physical shape of the car could change. These are renderings here, but the actual car was built as a prototype, and so the car gets longer, flaps move, it changes the wind flow, and so they're able to reduce the coefficient of drag. So again, using data and simulating how real world functions, but doing it in a virtual environment allows them to create a more economic vehicle. Same thing's happening on the safety side. We're working with Honda now, and this is showing, again, computer-generated simulation of a crash test. So again, we're modeling the physics of this, and the cool thing here is that we can now take apart the vehicle, right? Before it's ever even built, we can start to peel back layers, and we can see how the undercarriage is going to hold up in a crash. And the engineers can then iterate on their design. They can experiment and say, let's make the undercarriage a little bit thicker steel, or we can change the number of weld points and rerun the simulation and see how the car will perform. Now again, it's all about data, right? How good is the data then that's going in and coming out? And so what we've been able to do is iterate on these models now to the point where if we look at an actual crash test next to the simulated crash test, you can't tell the difference. And it's really been a remarkable breakthrough recently to be able to, again, do all this work before any car gets built and goes through this crash test. So engineers are able to iterate very quickly and then also be able to come up with a much better design. So again, this is how we've been working with the auto industry, from design to engineering and even sales and marketing, right? You can even go into some showrooms and put on a virtual reality headset and configure your own vehicle. But what I want to focus on is really data now and how the data is being used for artificial intelligence. And again, this is part of what this whole conference is about. And what I think is amazing, too, is you look at all the different areas that data is being used to teach machines to learn. And the kinds of results we're getting is amazing. In healthcare, being able to do cancer detection or early onset Alzheimer's. You guys probably heard about the AI chatbot that was getting people out of parking tickets. We have people who are using our GPUs to run algorithms to figure out how to brew better beer. In agriculture, the list just goes on and on and on. And it's so amazing. It's all fundamentally comes down to this notion of taking data and being able to do pattern recognition. If you even look at how new mobile apps now, you can do visual search. You take a picture of a scene, and the back-end system running on a GPU will analyze that image, figure out what are the objects in that scene, and be able to then go and search a massive database and come up with other alternatives. So what we're seeing, again, is an incredible shift from basic software algorithms to these systems that are becoming very intelligent and using various forms of artificial intelligence. Again, what's astounding is you look at recently, we have over $5 billion in investment going into AI startups. And there's this whole, I mean, this is a bit of an eye chart here, but the whole notion here is from all the research going on to the big players, Amazon and Google and Baidu and others, to all the startups, whether they're in automotive or not, right? There's a massive number of startups and that are, again, using this fundamental technology, then create new businesses, create new services, and then you have the big players, and in the auto space, it's virtually every automaker now is adopting AI and deep learning in one way or another. I think the cool thing, and I want to show this as an example in robotics of how this applies, but you have so many aspects of how the whole robotics industry and in turn autonomous cars is evolving, which all is fundamentally based on deep learning and AI. So the ability to understand language, the ability to do detection and recognize facial expressions or gestures, complete body language, all these things are pattern recognition types of operations, and even figuring out localization and mapping. So a lot of the work that's going on in robotics obviously applies directly to autonomous vehicles. Essentially, a car is becoming a robot on wheels. We as drivers, of course, know it's not an easy task to drive. There's a lot of complexity. Every single day, there's something new that comes up. It's crazy out there. You have different types of roadways, different scenery. You have different driving conditions, different weather. You have humans, the randomness of all of us trying to get where we're trying to get. I mean, just driving through the city, walking through the city, it's pretty crazy. And then you have all kinds of rules. You have emergency vehicles. You have different types of vehicles that behave differently. There's really no possible way to write software to drive a car. It's truly impossible. There's too many scenarios, too many if, then, else type of statements. And this is what's really been the challenge for so long. This autonomous research has been going on for decades. But just most recently, with breakthroughs in deep learning and the access to massive amounts of data, and the ability to train neural networks, we're starting to see some really significant milestones met. So again, deep learning, I think, is the key here, that you have the ability to have systems learn. And so essentially, what we want to do, and looks like this isn't coming through, so we'll skip it. But essentially, what we want to be able to do is have a system that can understand what's going on. And there's really two phases of that. One is a big data problem. We're training a neural network, and the way we do that is we feed it massive amounts of information. So if we want to teach a car how to recognize a car, instead of the traditional computer vision-based system, where we're going to write feature detectors and try to understand different aspects of that image, instead we're going to feed our neural network massive amounts of images of cars, of trucks, of pedestrians, of signs, and basically teach it its vocabulary, much like you would a child. And the way this works inside the neural network, essentially, is we have these layers. And we're basically trying to create a model of how the human brain functions with its neurons and synapses and the connection that goes on. In the case of an image or video, which is comprised of 30 images per second, the computer has no idea what's in that image. It just knows the pixels, right? Every dot has a numerical value that says what that color is. So what the neural net does in these algorithms basically break it down into its most fundamental pixel, and then we start to look at the surrounding pixels and start to figure out what's contained in that image. So the first layer you can see next to the vehicle is a layer that is basically looking for edge detection. And edges are really critical, first of all. If you think about, as you look around this room, what do you notice? You notice the edges where the wall meets the ceiling, with the boundaries of the screen, the posts, the podium here, whatever it is, that helps define objects. So this neural network first starts looking for edges, and then grouping those edges together to form elements, and then puts those elements together to form objects, and eventually it ends up with a car. Now, essentially, we do this on a massive scale. Millions of images get fed into a neural net, and we will train the system. So essentially, this becomes a massive problem, and it sometimes takes weeks or months to train. What we've done is we've put together tools for data scientists that are a combination of hardware and software to be able to put a massive number of our GPUs with thousands of cores per GPU into a server rack. So this is a new box we introduced. It sells for $130,000. You go, whoa, that sounds like a lot. The reality is it's the equivalent of 250 traditional servers. And so we can deliver in this one box 170 teraflops of processing power for data analysis, data analytics, and deep learning. So again, what we're doing is by an order of magnitude, really, at least, reducing the amount of time required to do computation on any kind of deep learning and data sets. Specifically for autonomous vehicles, we have this kind of basic structure of what we need to do, though. First thing, as you see, the Google cars or other self-driving cars around San Francisco on the peninsula, they're laden with sensors, right? We have to add radar, LiDAR, more cameras to be able to replace our eyes and ears and our senses. Massive amounts of data being collected by these sensors. And what we need to be able to do in real time is understand what those sensors are detecting. Again, what's a car, what's a truck, what's a lane, what's a sign, what's a pedestrian, and the list goes on and on. So once we're sensing, once we're getting all that information in, the key thing is to be able to run this neural net in real time to be able to make sense of all that data. And in addition, what we need to do is take data coming from a map. So you've probably heard about a lot of map companies becoming prominent, whether it's here, the consortium that was bought by Daimler and Audi and BMW, to TomTom, to Garmin, to Zenrin. Mapping is critical. And again, it's all about the data. We need to have an understanding of our environment that's static. And then we need to be able to understand what's in our environment that's moving. And so essentially, we need to build a full 360-degree understanding of what's going on around our car as we drive. So we create an environment model. And what's interesting is this kind of goes back to the video game world. Inside the brain of the self-driving car, it has to form this understanding. It has to create essentially a whole 3D model and be able to sense what's going on around the car. So essentially what we've done is we've brought our architecture down into the car. This is our Drive PX. And this is being used by over 80 automakers, tier 1 suppliers, startup companies, and universities. It's about the size of a license plate, but it has the power of 150 of these MacBook Pros. So again, it's designed to be able to take all the sensors, 12 camera inputs, LiDAR, radar, ultrasonic, all this data, gigabytes of data coming in every second, and being able to make sense of it using neural nets. So again, we're using data to write software as opposed to actually having to hard code the algorithms. So let me show you a few examples here. This is work that we're doing with Mercedes. They have a lab here in Sunnyvale. And again, what they've done is they've trained the neural net in advance. And now as they drive the car, they're able to do multi-class detection with cars, with pedestrians, with signs. And this becomes critical. This is how they build a whole environment model of everything that's going on around the car, and then can plan the path to drive safely forward. Now, a key thing here is, again, just identifying objects isn't enough. We have to really have a full understanding of where it's safe to drive. So the next example, again, on the same neural net that was trained, different version of the algorithm then lets us calculate what's called free space. We're doing per pixel segmentation. So every pixel in the frame essentially is classified. Is it a car, truck, sign, pedestrian, sidewalk, or in this case, street, which is purple. And so this gives us a really clear understanding of where that vehicle can navigate, where it's free to drive without hitting anything. Again, though, I think a key thing is it's not just good enough to be able to sense all these other objects around, but we have to be able to do it in a whole variety of different conditions. This is work we're doing with Audi, and in this case, again, they trained the neural net actually on good weather. And what we wanted to do was test and see, well, what happens in a snowstorm? And the reality is here we've been able to achieve better than human levels of perception throughout these benchmarks and these tests so that the car can detect things way off in the distance even before a human would be able to know that there was a vehicle there. We're also really focused on driver behavior and being able to do things that humans, often when they're distracted, not paying attention, may fall asleep, aren't able to do. One of the things that Audi did, and this I think is a breakthrough here, is the ability to now achieve better than human levels of perception. In this example, Audi had been working for 2 years with a smart camera company. Essentially, they wanted a system that could detect street signs, among other things. But in this specific example, we had 2 years of hard-coding computer vision algorithms compared with when they finally got our deep learning system recently, they spent just 4 hours training it. So 4 hours of feeding their database of tagged signs into the neural net. After that 4 hours of training, they achieved a better level of perception than 2 years of engineers working on hard-coded algorithms. The benefit, of course, here too is that they can continue to enhance it very easily. More data increases the accuracy and increases the robustness and the vocabulary of what the system knows. For example, if they go to Japan now and they have a whole different library of signs they need to recognize, they don't have to go back and recode anything. It's just training that neural net to recognize the Japanese signs. So feed it new data. Essentially, the software writes itself, and now that fleet of vehicles can recognize all the Japanese street signs. I think we're going to see more and more over-the-air updates in vehicles. I think people are generally familiar now with Tesla. We worked with Tesla very early on. We're a partner of theirs on the 17-inch touchscreen, on the all-digital instrument cluster in that car. And what they've been able to do is, over the life of the Model S, for the last 4 years, continually doing over-the-air software updates to make the car better, to give it new features and new capabilities. As we're talking about deep learning now, there's going to be this ability to continually update these vehicles and make them smarter and smarter. If we look at the landscape now, this marketplace is going crazy, right? You have everyone from Uber to Google to Volvo, GM. Everyone, first of all, has labs here in Silicon Valley. All the global automakers, if you weren't aware of this, they all essentially are all up and down the peninsula with research labs. So now we have startup companies and a lot of very large companies, internet companies and others, that are getting in this space. Huge timeline of investments in the last year being made in autonomous driving, and more specifically, though, AI. You have companies like GM buying Cruise, guys here in the city that have been working with deep learning. Uber's using deep learning. Google's obviously using deep learning. So again, the ability to get data is becoming a real differentiator. And that's going to be, I think, one of the key challenges that small companies have versus the big companies is capturing data. You need a massive amount of data to be able to train these neural networks. I think one thing we're starting to do, and this will help to augment, is simulation, right? We can simulate driving scenarios and use that simulated data to also train the neural net. This is going to be really key because as we need to drive millions, if not billions of miles to really validate the neural networks, a lot of that driving does not include the kinds of incidents that we really need to prevent. And the only way to train a neural network, really, is to provide it information that's relevant. So we're going to see driving roll out on the highway much sooner than other scenarios because we can get a lot of data and train the neural networks very well for highway driving. But in a city or in a neighborhood where you have a ball roll into a street and a child run out in front of it, we need to have a very robust system for training a neural network how to detect that kind of situation. So this is where we can use simulation as well. Simulating a lot of the corner cases, simulating a lot of potential accidents to train neural nets to then do the right thing. And again, Google's announced that they're doing a lot of work in this space, simulating over 1 million miles of driving a day. One of the things that we've worked on, and most recently in New Jersey, in one of our research facilities, we're showcasing a vehicle that we modified. And essentially, we took a stock car, and we added a variety of sensors to it, predominantly cameras. We want to do a vision-based system and test it, and drove the car around to train it. Now, when we first took the car out, the neural net was basically empty. It didn't know anything, so we had to train it. Now, this isn't the way it'll work for consumers. Once you get an autonomous car, it's going to have a fully trained neural net. But in this case, what we wanted to show was taking data that we're capturing in the car, then sending that back to the cloud, sending it to our DGX, our deep learning server, and being able to train the neural net, and then do an update back to the vehicle to be able to then put those smarts into the brain of the self-driving car and then give it a test. So this video sort of shows that. We started testing in February, and this was on a proving grounds by our office. And first time we take it out, it's like a teenager, right? It doesn't know how to drive. It hits cones, it starts driving, it can't stay in the lane, right? It hits the trees. It's the teenager, it doesn't know how to do anything. And the driver had to take over. So what we did was we took it out for 3,000 miles, basically 72 hours of driving over the course of several weeks, and trained it. And then once we validated that neural net model, we put it back in the car, and now you can see the car can recognize cones, drive around construction zones. This was done in New Jersey, where they have no laws about autonomous driving, so this is perfectly legal. We're driving on the Garden State Parkway, we're driving on country roads, but I think what's critical here is that there's no lane markings on some of these roads. And so this system was not created to recognize specific items. It wasn't trying to detect a specific car or a lane marking or a specific sign, but rather what we did was take in a holistic approach of the entire scene and then be able to map from that whole camera view and sensor view to the steering commands and really do what's called end-to-end deep learning. Major breakthrough, and I think we're going to see a lot of this in the future. Now, moving forward, we see a huge adoption, and this is data from IHS, so market research firm, and really showing massive growth in terms of AI coming into the automotive. Not just in the cockpit, where we're starting to see things, obviously with Siri. BMW has introduced some gesture recognition and other technology. But we're going to see more and more human interaction in the user experience of cars. So neural nets being trained for voice, gesture, driver monitoring. It's really key to make sure that as we start to go into this transition for autonomous vehicles, that the car knows what the driver's up to. Is the driver paying attention or not? And if that driver is not paying attention and needs to be, then there will be alerts or the systems will shut off. And then we're going to see, again, increased AI, increased deep learning, increased need to collect and process data throughout all vehicle lines. If you look forward, basically, again, every automaker has declared that they're going to have 2021, 2025, whatever the timeline is, they're moving towards autonomous vehicles. And we have companies like Google, like Uber, rumors about Apple, that are really accelerating that pace and forcing automakers to bring this technology to market sooner. I think we all see huge advantages of it. It's going to really free up a lot of time. I mean, on average, we spend 42 hours a year stuck in traffic. It's going to give you a lot of flexibility. It's going to enable mobility for people who can't drive, elderly, children, any disabled who currently don't have that flexibility and mobility will be freed up. And it's really going to really transform a lot of different businesses. I think one of the things that's kind of cool, this is more of a fun application, is auto racing. And I don't know if any of you guys have heard about Robo-Race, but this is an event that's planned starting in the 2016-2017 season as part of Formula E, the electric Formula Race Series. So this is a full-scale Formula One style vehicle to be unveiled this fall. You notice there's no cockpit, there's no driver, right? This will be a race series where there's 10 teams. Each team gets 2 vehicles. Every vehicle is identical. So this was designed by Daniel Simon. He came out of Bugatti. He's been in Hollywood. He designed the vehicles for the Tron movie series. He designed all the vehicles in Oblivion, the Tom Cruise sci-fi movie. And so now he's taking his virtual vehicles and bringing them to reality here. So this will be laden with radar and LiDAR and cameras and sensors. And our Drive PX2 will be the brain of every one of these race cars. And so what I think is really interesting about this race is it's not about the tires, it's not about the engine, the motors, the batteries. Every car is identical. The only thing that's different from team to team is the paint on the vehicle and the software. So each team is going to be developing their own algorithms, will be training their own neural nets, and basically loading software and letting these cars, all 20 of them, race on the track simultaneously at very high speeds. What's also going to happen is some of the race slots are going to be available to the broader community. They're going to announce a competition where independent teams can be formed, universities, corporations, and you can actually develop your own software stack and test it in a virtual environment, and the winners are going to gain a spot on the actual track. So this will be something really exciting. Again, I think autonomous vehicles are coming very soon. There's a lot of legislation, a lot of regulation that needs to be in place to ensure safety, and we're all for that. We're working with a lot of federal agencies. We're trying to not have the state agencies get too involved because it becomes a disaster if all the 50 states have different rules. It really needs to be uniform. But the goal is to, again, be able to bring this technology to market as quickly as we can, but make sure that's done in a safe manner. So with that, I'd like to thank you and open it up for questions.
Thank you very much for the excellent talk. I have a quick question regarding the simulation. So for example, for very rare situation like Tesla's fatal accident situation, it's not something maybe driving even 100 million miles to drive into. So are you thinking in those cases simulation would be really helpful? But following up on that, how do you imagine or create those simulations?
That's a good question. So the question was on how do you handle corner cases? How do you handle events that hardly ever occur? And the reality is, yeah, we can use simulation to make sure that the neural nets get trained to understand what's a truck versus what's a billboard, things like that. And again, simulation, actually there's a number of gaming engines. So the whole environment that gaming companies use to build their worlds, they're actually moving into this simulation space. So they can create all kinds of different scenarios. The thing that I didn't touch on, but it's part of what you're saying is, we also train the neural nets from a behavioral perspective too. And so what we want to do is, by capturing more data, really drive like a human drives, not like a computer would drive. Right? Our car here, with the amount of computing on board, can drive very precisely. Right? We can sense exactly the distances to other objects, the exact speeds of these other objects, and we could weave through traffic if we wanted to. We could stop it on a dime if we wanted to. But no passenger in the vehicle is going to feel comfortable with that, nor are the other cars around going to like that. So what we have to do is really train the car to drive like a good human, not just any human, but a good driver. And so we can model behavior into that. So if we sense a parked car with the car door opening, what do you and I do? Well, hopefully you slow down and stop because you anticipate that door is going to open, or you change lanes. The radar is just going to sense this blob and is not even going to know the door is about to open. But we can build that into the neural net so we can anticipate and take action. If we see a motorcycle splitting lanes way back, our autonomous car can naturally shift over like we as a human would do if we were paying attention. So we can both build this into the models and use simulation to create those models. I think a key thing here, though, is the notion of the car getting trained. So it's not that you driving your car are basically going to be training your car. The data is all going to be collected and processed, and data scientists will be involved in making sure that what's getting pushed back out over the air to the fleet of vehicles has been certified and validated. So I think that's a real key thing, that we're going to be involved in training the vehicles, not the general public. Question back there?
Thank you for your great talk. During the self-learning process, what kind of feedback do you give to the system? When you showed when it starts, it drives really awful, but it starts learning. What kind of feedback do you provide?
Essentially, it's not unaided learning. It's not like we just feed data. So initially, things need to be tagged, right? So we need to teach things. This is a car, so we've tagged those, the signs, all that. In the case of this end-to-end system, what we would do is we actually mapped the sensor data to the steering wheel feedback. So the corrective action was the steering. So there were times when it drove by itself, and if it didn't get corrected, then that was interpreted as good data. If we had to correct it, then that was the reinforcement learning taking place there.
What do you see as the other major sort of constituents that will be its own increasingly competitive sort of sub-sectors? What are the other domains of technology that you think will really flourish as we figure out what works out best here?
Yeah, so the question is basically, what are the domains, what are the areas that need to be in place? And you're absolutely right. It's a very complex ecosystem. There's no one company that has this solved. And so what we've tried to do is, again, you need to be able to sense. That's the first thing of robotics, sensing. So I think the big challenge automakers have right now is, what is the right mix of cameras, radar, LiDAR? And I think everyone's going to come up with different ideas on that front. And there's many LiDAR companies now. And the key issue has been, how do you reduce the cost? Because the spinning LiDAR that we've all seen on the Google cars, $70,000, that's now coming down to maybe $10,000, but they might have 4 of them on the car. And so we're going to see solid-state LiDAR. I don't have the answer for that. I think it's just, this is a new industry. It's very rapid iteration. But I think one thing that's sort of universal that we've discovered is the requirement for computing is enormous. I mean, even our platform that we announced at CES, people love it. It's replacing 4 PCs that are in the trunk of a lot of these prototype cars, but they still want more. So we're constantly forced with delivering higher levels of performance, smaller, less energy consumption. The reality is there's 100 ECUs on a car today. And the car makers are going nuts because of the level of complexity. So we're really trying to reduce the amount of complexity, reduce the number of silver boxes in the car, and really convert a lot of those things into apps. And again, I think this is where it's going to be interesting, is that your blind spot monitoring system, or your lane departure system, or these other things that are individual physical boxes that get put in the car and all wired together, are going to become apps, right? You're going to have different bits of software that are doing different functions in the car. And much like on your phone that you download and get a new app, I believe in your car, eventually you'll be able to say, you know what, I didn't buy blind spot monitoring, but I can touch on the screen and do an in-car purchase, and now my car has blind spot monitoring. And I don't think that's that far off.
Thanks for the good talk. My name is Wei Li from Autodesk. So my question is like, in the future, it's definitely, it's almost for sure, the self-driving car is going to be very prominent. But my question is like, with enough sensor, with enough data collected from car, not only from the sensor which control the car and the steering the car, but also sensor measure the different physics in the car. Can we leverage the data to design better car?
Yeah.
Any comments on this kind of new application of data?
I think so. And again, I think we see some of that coming from racing, right? The racing guys are constantly trying to use data to streamline how they design the cars, the driving dynamics. I think for autonomous cars, that's less important. I think we always want to figure out, how do we use new materials to make cars safer? How do we model the physics? The reality is that these cars are going to be very cautious, right? No automaker is going to have an autonomous car drive aggressively, like a Porsche or Lamborghini driver may be going down the highway. And so to me, I think the driving dynamics, we want to have a safe, enjoyable experience, but it's going to be in cities, it's going to be commuting and things like that, as opposed to real high performance. And one of the things, so you're at Autodesk, I don't know if you're familiar with this project. I think it's fascinating. There's something called HackRod, and Autodesk I know is involved, we're involved, and they're basically using AI for generative design. So they're putting a lot of parameters in constraints, but then using AI to actually design parts of the car, as opposed to a human designer to do it. And so I think, again, this is a whole other field where we're going to see AI involved and working alongside humans, not necessarily replacing them, but working alongside in things like design and any kind of research.
Yes, thank you for your work. I'm in the team.
Thank you for your talk. So my question is that I know in the future, can we not only have self-driving cars, but also have self-driving cars with different personalities? Let's see, we can have calm driver John or aggressive driver Jason or something like that.
So yeah, I mean, I think it comes down to the behavior. And we can basically train a car to drive like anybody. Now, whether that's a good idea or not is up for debate. I think we all know the answer to that. And so again, think about it. The brand of car companies is going to be defined by how well does their autonomous car drive? How safe is it? How reliable is it? What situations can it handle? And so this isn't going to be something that car companies are going to play around with. And again, I think it's going to be very conservative. There may be some slight adjustments, just like when you have cruise control today, right? You may have 3 different settings. How close do you want to follow that car? Or traction control, right? Do you want to stiff, or do you want to smooth? But again, I don't see a huge range. An autonomous Porsche may drive differently than an autonomous, Honda. Who knows, though? But I think, again, conservative will be the nature for at least the traditional car companies. You may see some variability in some startups.
Thank you.
I think we have time for maybe 1 or 2 more questions.
So, NVIDIA to me is a company that develops great graphics. But by developing algorithm like this, it feels like you are going to some kind of vertical application space. Can you comment on that?
Yeah, so NVIDIA, the question was, we're a graphics card company, what are we doing here? I think what you've seen is a sort of a broadening of what we do. We started in graphics. We moved from gaming into professional graphics. So essentially, every car, every plane, every consumer product is designed using NVIDIA graphics today. So the graphics part, is what we're known for. What happened over a decade ago is people realized that the GPU, the graphics processing unit, with its massive parallel processing capability, could be used for things other than graphics. And so we started putting our GPUs in servers, in the data center, in other workstations to do number crunching and run algorithms. And so that's been a huge part of our company. Maybe not a well-known part, but our country's fastest supercomputer here, Oak Ridge, is comprised of 17,000 GPUs. And so parallel processing has become a big part of NVIDIA. And a decade ago, we took our graphics into cars for doing things like infotainment and mapping and rear seat entertainment. But again, much like the GPU moving out of graphics there, we've discovered that specifically for deep learning and AI, there's an application. Self-driving cars is one of the most complex problems to solve. And that's really, as a company, what we like to do is solve hard problems. So again, we're not building cars. But what we've done is create this platform. It's an open development platform. And so our hardware, plus a lot of software, is what we make available to the auto community for them to build their applications on. And it's the same model as the gaming industry. We don't write video games, but we create the systems for Electronic Arts and Ubisoft and all the others to build amazing games on. Okay, one last question, then we'll...
Danny, I have a question about thank you for a great talk. I have a question about the current state of implementation. Are autonomous vehicles being used anywhere today? Are there closed communities like military bases or college campuses? Are there other countries where they're being used today? And what's your prognosis of how this is going to proliferate in the market?
Real short answer, and then I'll be available out back if anyone wants to ask more questions. The answer is yes. There's a lot going on in closed circuit testing courses. A lot happening outside the US. We're working with Volvo. They're going to be doing a real trial with real cars, real customers next year in Sweden and then UK and China. So that's actual Volvos with our Drive PX inside, fully autonomous. And Volvo has said they will accept full liability if anything happens when those cars are in autonomous mode. Next year, our Audi project hits the streets on public streets in cars people can buy for traffic jam assist. So again, it's these steps toward full autonomy, but again, the car will drive itself. And there's numerous others going on closed courses. All right, thank you very much.